Hey guys, this is Rachit Jain. This is the first in line of a long queue of videos that I have developed to give you a strong fundamental base in this ever popular field of probability. The agenda for this video would be to start with the fundamental terminologies involved in probability. My effort would always be to maintain practical understanding for simple and complex subjects without degrading the quality of content that I wish to deliver. So, without further delay, let's get into it. Let's start with random experiment. We have been hearing this term since the day we have heard something about probability. So, I want to give a simple definition that could stay with you whenever this special phrase comes in any discussion next time. A random experiment is the one in which all possible outcomes of the experiment are known in advance. The outcome that would come is not known beforehand, and the experiment can be repeated under the same conditions, though different outcomes are possible. The outcomes shall still be the same, for example, a head or a tail for a coin toss, but the outcome for any given trial can be different, thus giving rise to the randomness of the experiment. Next comes another common term associated with probability, and that is sample space, notated by a capital omega, popularly called as the universal set. It is the collection of all possible outcomes of a random experiment, and these outcomes are called samples. For example, in the random experiment of tossing two coins simultaneously, we can have heads and heads, head or tail heads or tail tails, and these are the four samples that constitute the whole universal set, or the so-called sample space for this experiment. Now in school, we often limit ourselves to these two definitions, but to ensure that we remain a bit more rigorous without losing on to the understanding, I shall introduce the concept of sigma field of omega, which is notated by capital S. It is a or any collection of subsets of capital omega such that the following conditions are met. First, phi, that is the empty set, must belong in the capital S. Secondly, this sigma field, that is S, must be closed with respect to complement operation. That means if some event A belongs to S, then its complement, that is A complement, would also remain in S. Here you can recall what complement over the universal set means for any set A. And finally, S must be closed with respect to countable union. So if some sets belong to S, then the union would also belong in the same set. But wait, why are we learning all this, right? Rather than defining probability to be just P of X equals something between 0 and 1, I wish to give you relatively stronger footing in this domain that shall help you in school, college, higher studies and beyond. To ensure that you understood what a sigma field is, let's try the following examples. For example, S is equals to phi and omega. This is trivially valid. For example, S is equals to phi, A and omega. This is not a valid set, sigma field, because the complement of A does not exist in this set. And hence S is equals to phi, A complement and omega. This set is a valid sigma field. But suppose omega is heads and tails for a coin toss, and the sigma field be the empty set and the universal set. This is not the power set. Well, you can say that the power set is kind of a sigma field, but if you could recall, sigma field may or may not contain all the subsets of your set or the possible outcomes. Hoping that you got the distinction between sigma field and power set, let me strengthen that with the true definition of the same. Power set is the set of all subsets on a set on which it is applied. So the set of all subsets. For example, for a simultaneous toss of two coins, the power set would have all elements including the empty set, the universal set, heads and heads, and its complete complement over omega, tails and tails and its complement, and so on. This is the reason why for huge sets like, for example, the real set, we do not actually consider the whole power set, because that is, the sigma field will be a shorter set and would be used for statistical purposes. Again, why do we need the sigma field? Why not any other set? So to define probability, we need to understand we need to have the following three conditions which are made possible through the concept of sigma field. First, it is closed with respect to the complement operation, and that is what would be used to define probability. Also, it is closed under countable unions. And finally, as I said, we need not have to use the complete power set to define probability. What we need is a valid sigma field and our work is done. So in summary, it is important to take away the following points. Capital Omega is the collection of samples. A sample is not same as an event. Secondly, the sigma field notated by capital S is the sigma field of capital Omega, and its elements are called events. For example, for a coin toss, heads and tails are possible outcomes and are called samples. However, heads is not an event as it is. The singleton set, also called the elementary set, having heads as an element becomes the event. So when you toss the coin, what comes as the outcome becomes the event. Although the possible outcomes, that is heads and tails, are not the events as such. Hope this video added some knowledge and value to your foundational terminologies of probability. In the next video, we'll go on to defining what exactly is the definition of probability. If you like the content, don't forget to like the video and subscribe to the channel. Till then, stay healthy. Rachit Jain signing off.